Welcome. Today we are solving the 1D heat equation on a thin rod of length L equals 1. And the governing equation is partial T Nk partial square U to the partial x squared, where the function u xt is the temperature at position x and time t, and k equals to 1. And the physical scenario is simple. The rod starts with an initial temperature distribution of function u x0 equals to function of x equals 8 sine of pi x per L, and both ends are held at 0 temperature for all time, so function u0t equals to 0, and function of ult also equals to 0. We are going to analyze how this initial heat diffuses along the rod over the time and calculate the temperature at x equals 0.5 and t equals 0.05. Now we're going to separate the variables. Function of u with the variables of x and t equals x of the x variable times t of the t. Stop substituting into the heat equation equals x times x derivative of period per derivative of time equals into k period of t times t squared of x and derivative of x squared. Now dividing both sides by this, that we get 1 per t times derivative of period and derivative of t equals to k 1 per x t squared x dx squared, and that equals to minus lambda After that, we're going to solve the special ODE. Now the special equation becomes d squared x divided by dx squared plus lambda of times x equals 0. We set lambda to pi when n times pi per length squared, so it becomes x and x equals to a and sin times n times phi times x per length. So the boundary conditions becomes x0 is 0 and x L than 0. Next, we're going to solve the temporal ODE. The temporal ODE becomes derivative of period divided by derivative of time plus lambda times k times period, that equals to 0. Solving this gives t of n t equals to c n times times exponential with the power of minus k lambda t, that equals to c n e with the power of minus n phi per length squared times t. This exponential decay reflects that heat dissipation as time increases, the temperature diminishes. And also we're going to do superposition and initial condition. Combined solution gives the general solution u x t equals 2 sigma to the infinity to the n of 1 dn sine times n pi x n pi x per length times exponential with the power of n pi per length squared. And after we apply the initial condition, it becomes u x 0 equals to 8 sine phi x per length. This means only the first term is present with b1 equals to 8 and all other bn are 0. Thus the solution simplifies to u x t equals xt equals to 8 sine pi x per L times exponential with the power of pi per L squared times t or time. Now we are asked uh sorry we are asked to find the temperature at x equals to 0.5 and t equals to 0.05. So first compute sine of pi times 0.5, that equals to sine pi per 2, and that is 1. So the function of u 0.5 and 0.05 is 8 times 1 times exponential with the power of minus 5 squared times 0.05, and that equals to 9.8696, and then times that becomes around 0.4935, just about 0.4935. Thus u 0.5 0.05 equals 8 times exponential of 0 minus 0.4935. That roughly becomes 8 times 0.6106, and right about 4.8848. So the temperature is about 4.88 units. So in summary, we solved the 1D heat equation using the separation of variables, applied boundary and initial conditions, and found the temperature at a specific point and time. This type of analysis is crucial in real-world applications like thermal management in electronics, cooling systems, in engineering, and even material science. Thanks for watching and see you in the next lesson. Thank you.